In the last video, we introduced this absolutely critical definition about eigenvalues and eigenvectors, and we said, okay, well, if we have a matrix A and we can find its eigenvector and eigenvalue, they have to satisfy this relationship where we take the matrix times its eigenvector and say that that's the same as the eigenvalue times its corresponding eigenvector. Okay, and then we went through an example briefly to illustrate this. Now, here we just we ended up finding them, or saying like, okay, this is what we have. We found those through iterating the system, and in general, we're going to have more sophisticated methods to find these eventually. Okay, but this video, we want to talk about a matrix being diagonalizable and an eigenbasis. So when we talk about diagonalizable, all that means is that it is diagonal. Okay, so as you can see here, I have a little sketch drawn. We have a matrix, and on the main diagonal we have values, and on the off diagonal we have zeros. Okay, and in fact we might even conjecture that if we looked back here, this A matrix, we saw that 1.1 and 0.9 were our eigenvalues, right? And those happen to lie along the diagonal, and our off diagonal was 0. Maybe we'll see that. Okay, but if a matrix is diagonalizable, what that means is that A has a basis of eigenvectors, and when we use this phrase so often that we just call that basis of eigenvectors an eigenbasis. Why? Because we can. Let's make everything eigen. Why not? No, but seriously, we just call it an eigenbasis. And so we can see that in our last example, we had two eigenvectors. We said that they formed a basis earlier, so we can say that the eigenbasis is our two eigenvectors 100, 300, and 200, 100. Okay, and then when we have this eigenbasis, then we can say it's diagonalizable, which means that it can be similar to a matrix where we have the eigenvector or eigenvalues along the diagonal as we saw above. So there we go. Okay, and actually this has an extremely important implication. It does mean that if we have a matrix A that is not diagonal, we can diagonalize it, or we can diagonalize it, or it can become diagonal by finding its eigenvectors and eigenvalues. Okay, and we saw this before when we did change of coordinates, but when we have this diagonal matrix, its diagonal is going to be precisely the eigenvalues corresponding to matrix A. Oops, I wrote A, and this meant lambda n. Okay, and when we have this occurring, then we say that S is really the eigenvectors. Okay, so this is a very short video and largely conceptual because we have to do there's so much calculation to all this that we just need to do that off screen. So we'll get some practice with this during group work.